I'm going to be talking both about F# and F*. It will be confusing. I will get it wrong. I always do. And they are close cousins, so you're going to see that there's more than one reason for them to be confused. So the thing that always, I don't know, it doesn't really irritate me, but there's a real reason for me to ask this question. This is a polyglot talk because of the influences that are coming into F# and F*. They are different, but they have a lot of overlap. And there's a lot of influences they also impose on the places where they have affected the industry, as in both in languages and in terms of technology that they support. So you'll see a little bit of buzzword bingo, but I want to see a raise of hands of who here has actually developed in either F# or F*. Wow, fantastic. There's more than 0. That's great. And if you've experimented with other functional first languages, and I'm talking about Scala or pure functional languages like Rock or Haskell or anything in that echelon, has anyone done functional programming? All right, that's great. So this is going to be a multi-paradigm talk as well as a multilingual kind of name-dropping talk. So I'm actually going to be doing a little bit of tracking of this. And this goes to that thing of where the inputs are coming from and where the outputs are going to, and then also the things that I had exposure to early in my career that kind of influence the way that I see things whenever I look at them. So I'm going to try to disambiguate that a little bit. One of the weird things about talking about compilers, maybe I should ask, is who here has worked with MLIR or LLVM? Anyone developed for Swift? Yeah, so you've probably, and of course Haskell will also funnel through LLVM. So you will have brushed up with maybe one side of this or another side of this if you've only been in the .NET side of the world, or if you've only been, and show a little bit of JavaScript that's being run by F#. And then, of course, there are these folks that live in the Swift and Haskell and other worlds that go directly to LLVM, where they're going to recognize certain things, but other things are just not going to be even close. So hopefully I can find enough to irritate all of you, and everyone will be equally, anyone that knows one of these terms here will be equally irritated by the fact that I didn't give it proper justice, because this is going to be a speed run. So first, of course, I'm going to talk about myself. And the picture that you see up here in the upper left is from about 1994. This is before my foray really into full-time software development, but I was kind of at the software and hardware boundary because of that instrument to the right that has got the guts opened up and spilling out for everyone. And the memory Moog instrument was run on a Z80 processor, and eventually we modified it, changed the quartz clock, put in a Z80 or 8088, I can't really remember. It's been that long. To speed up the clock and to improve the memory as well as some of the interrupt structures so that you could have a better musical experience with the instrument. The memory Moog was actually a failure when it was first designed by Norlin. It was after Bob Moog had actually left the company. So in case you don't know, the person in the middle is the world famous Bob Moog, who invented the entire Moog ecosystem and was really kind of one of the forefathers of the modern electronic music industry. To that end, he's also a PhD in engineering physics, and one of the things that he was asked to do was to help write the electronic music entry for the Encyclopedia of Applied Physics, and I helped him edit that when I was a research assistant for him in college. And one of the reasons why I brought the table of contents here is because this little bad neighborhood where it talks about computer music, and it also touches on some of the technology that Kurzweil gets into the accuracy of floating point calculations, the importance of it not only from an academic perspective, but it just happened to be that it was really important for audio at that time in a way that I really didn't understand at the time. So we spent a lot of time going through that section, and I thought he had emphasized that within the entry for the encyclopedia because he previously worked as a VP of R&D for Kurzweil and just knew the territory really well. But it turns out it actually is really important. And when we touch on some of the things downstream, this will actually come back to haunt us or come back to inform some of the reasons why I'm doing what I'm doing with the Fidelity Framework. And of course, that last little bit is Next Computer, one of my research projects. I got funded during college, ended up with a Next Computer and doing a little bit of Objective-C and C and C++. And that was really my first compiler project to build a MIDI interface out of the SSI port that's on the 5601 that was on the Next Computer. And that was such a bad experience, I have not touched compiler development until about a year and a half ago. So yeah, we're talking about early 90s. So that was ancient days. So before I get into what I'm specifically doing with F# and taking it through MLIR and LLVM, I want to talk a little bit about just F# writ large. And that's because both its influence on the .NET ecosystem as well as the influence that it took from other ecosystems outside of OCaml, and we'll see in a minute that this actually is, if I put a check mark for every time OCaml was mentioned in this talk, or should be mentioned in this talk, there'd be a ton of check marks around OCaml because of all the shared edges that it has with a lot of other stuff. And the Fable compiler is a community effort that came in about midway through the life of F# that has given it a renewed life and was actually one of my inspirations, which we'll also see in a minute. The Fable compiler is really designed for, originally designed for JavaScript. We're going to focus on F# proper and .NET. And the primordial times of the .NET framework, kind of coming out of basically Microsoft being sued and them having to create their own runtime with garbage collection. And Don Syme was instrumental in building .NET generics. And so the idea of generics proliferating through a lot of these languages kind of came out of that. And then the first official release. And the 2007 is interesting because async was added, and that's when async and reactive kind of became more of the lingua franca that ends up kind of permeating throughout the different echelons of programming languages that were being developed at Microsoft Research that then went out into other areas. So at the end of this talk, there's a link that I put for a QR code to the History of Programming Languages paper that's about that. So we'll move forward to a certain degree. The task in 2012 being added to .NET was something that was both for C# and for F#. But F# was used to prove that infrastructure. And then a year after, they started with the F# Software Foundation. And I spent a short time on the board with the FSSF a few years ago. And then in the .NET Core era where F# and .NET becomes more open and cross-platform, you end up seeing wider use. And it happens to be that when you go to Fable, about the time the .NET Core goes multi-platform, you'll see the Fable begins to get some attention, and Alfonso Garcia Caro just did a yeoman's work in being able to do, in the slug line for the Fable compiler is, F# you can be proud of. Sorry, JavaScript you can be proud of. See, I just did it. So the basic idea was to take all of the optional type hinting that you do with JavaScript, and it actually becomes imposed on it by F#. So you don't really have to look at it, you're just writing F#, and then it just generates proper JavaScript. So this story continues to develop and expand. Tree shaking is a story we're going to talk about a little bit with what I'm doing with MLIR and LLVM. And then really interesting in 21 and 2022, there's other targets, and I think this is kind of part of the outcome of like the COVID dark times where people were really kind of just deciding whether they want to do some interesting things. So Fable now has, at that point, more targeting that it's aspiring to with Python, Rust, and Dart, and those are still in development in certain cases. And I think last year TypeScript was added. So I see the symmetries and the shared edges between TypeScript and F# being significant. So I've already done a lot of name dropping there, and so hopefully I've gotten everything. Sometimes I don't. There's actually an Erlang mentioned there for F# that I missed, and that was from early days. One of the things that F# did to go beyond OCaml was to adopt the mailbox processor from Erlang to be able to express agent or actor models where you could have encapsulation. And I look at it as a form of a sugared async or a sugared continuation. But it's really important for some of the things I'll be doing downstream where I'm fully developing it into a model of an actor system with a control backplane behind it. So now it's time for a demo, which is the reason why we went through all of this to make sure we could run this on my machine. But I want to take a pause for a minute and talk about the shared, more than a shared edge between Fable and F#. They actually interlock really well, and that was due to the work that was done by the Fable team, where you can actually create a shared library where the .NET library gets compiled from the same code, goes to Fable, and creates the interfacing that JavaScript then uses. So on either side of the wire, they have strong typing for both what's transmitted and what's received. And this is a bunch of gobbledygook that I just used to fill the page because we're going to look at the end result of what this looks like with the application that I built. Give me just a minute to bring up the right thing. Oh, here we go. So this is an application that I built that's a magnet site thing. We don't see a lot of traffic on it. We're not expecting to see a lot. But the basic idea is that this on the front end is just a React SPA. It's fairly garden variety, a really giant monolith that sits on a server, but we're doing the caching thing from Cloudflare. And on the other side, behind the scenes, is .NET, just regular garden variety, a .NET server with a Postgres and a DuckDB instance, which I'll show you why in just a minute. So I'm going to grab a fake address and stick this thing in here. We're going to show a quick little fun use of AI where I'm taking that address out of my thing and I don't want to bother typing, and I just want to send it into this form without having any of the stuff having to fill it in and type it out. So this is .NET running the AI extensions with, I think, kernel memory and a few other things, and llama.cpp kind of wrapped it inside of that to run a model that then is a modern BERT that takes this blob of text and brings it back in structured JSON that then gets fed back into the form. There's shared edges where that JSON object that's described as a strongly typed form, both on the client side and the server side, makes that really super easy. And one of the things that you would have seen, and you'll notice that like there's an event-driven architecture here that's just straight, single-page app architecture, is you can clear the form, and then you have these little toasts that pop up to let you know all the required fields aren't being used properly, blah, blah, blah. And then the cool little AI thing, and this actually goes back to one of the talks from earlier in the day where it was talking about semantic search and graphs, is you can actually, this is using the GICS standard. That's a whole block of text that you probably can't read because it's probably too small. But the idea was that the person would have the ability to tell you what industry they come from so you know what kind of conversation you're going to have when you have that conversation. So you can go through and look at this full retail and look at it by category, or you can actually go in and say, I don't know what I want to put, but I'm, say, part of a home builders. Sorry. All right, let's get the spelling right. I'm not used to being at this angle. I'm going to have to make myself about 5'8". So now I'm running the search, and what it's doing is there's a vector table with all these descriptions of the GICS, and brings back these categories by a similarity score, and it's basically just using cosine similarity. And I'm just grabbing the top 3. Usually you get one of the top 3, and then once you select this and decide, yay, verily, that's the one I'm going to use, it fills it in. So I can clear the form, and and then go on and use that. So the basic idea is the GICS table that we're feeding into the database that's then being vectorized is not only the category and the name of the category or sub, goes all the way down the line, is there's actually a statement in the GICS standard that actually describes what that category means. So now someone can just take and do a long description of, I own a series of hair salons, and it will come back with retail and cosmetics and a few other categories that are kind of in the ballpark. So this is one of those things where .NET is kind of providing this buffer to llama.cpp, and you make all these nice clean calls. And so essentially what's happening is F# is then being built into .NET, and basically the library that I'm depending on is actually written in C#. So you have 20 years of this long-standing, not only shared edges, but deep integration between F# and C#, so that anything that's in the C# ecosystem I get to use, but I get to now have the benefit as well of doing things within a nice, strongly typed API. So to that end, this is one of the shared edges that's between the React world and the F# world, where this definition, like what determines what a policy choice is both defined as an enumeration inside of the React app as well as in the back end. And one of the nice things, and people always talk about types being better than tests, what that means is this field that gets filled in that says this is the data policy choice can only be a certain number of things, which means you only have to test for a certain range of things when you're actually taking and trying to put some heat shielding around it. Now eventually what I'm doing within the Fidelity Framework is going a step further, and in some places being able to actually use proofs that then does more than what you would actually be able to do with testing and with types. So that's GICS, that's the interface, and then here is the mailbox processor. This is that thing that has been brought into F# from Erlang that is being used here actually as a semaphore. So it's actually not being used as like a freestanding running encapsulated unit of work, but it is sitting there. That's basically, if there's multiple people that are sending in events, it basically is creating a queue to take and write into the event store in JSON-B in Postgres. And then all of the things that I can do behind the scenes, I'm on schedule. Okay, so as an admin, I can actually look at that event store. There's that block of text that I sent as that fake person. Here's the structured data that came back for it, and I can see, in general, what, and I can go and show you from the user side. But there's also a view of this as well. And again, this is that little funky thing where it's actually going and doing a full retail poll from the event store and saying, give me all the events that are for me, and then just put them up here so I can see what's going on. And of course, if a person has done more work behind the scenes, you'll actually end up seeing more in the event stream. So you get all this nice infrastructure. I won't say for free because you still have to write for it, but everything that's there for interop with llama.cpp from the C# world you can access from F#, and you also get this really nice clean front end UI, fully responsive, and all the fun stuff that you would expect to see within React, and that nice SPA experience is there, but you have that common interface within F#. So everything's in F#, and then everything gets built behind the scenes to the appropriate target. So that was one of the reasons why I spent this much time talking about it, is folks don't always get a chance to see it. And it is a pretty substantial amount of commerce that goes out there. That's billions of dollars worth of work that's done in the .NET ecosystem, and likely millions, if not hundreds of millions of dollars worth of React work that's throughout the world, and a portion of that, particularly in Europe, is generated from F# for a lot of different applications that you see that you just don't think about because it's a garden variety SPA. There's also a story for .NET going to microcontrollers, which again is something that's a developing story over the past few years. There are several vendors and several open source community groups that are building for .NET to target to microcontrollers. Wilderness Labs is interesting because of their history with Xamarin and the Mono project, and they basically saved the Microsoft .NET ecosystem from obscurity by the acquisition of Xamarin coming in and it kind of informing the .NET Core effort in a way that allows them to be multi-platform and talk to Mac and to Linux and to Windows. But the server instance that I was running, my application I was running in Linux. So this is basically, again, another story where F# is wrapping C#, and we're getting units of measure, but it's done in a C# way where the units of measure are actually part of the runtime. So this is kind of a good news, bad news story. In F#, when you're using units of measure, they get compiled away and you're not paying any cost for that. Here in this, because where they're using the Mono runtime, which is the free and open source, or another open source version of the .NET runtime, they're putting everything basically inside of state machines, inside of allocated units within the runtime. So, but it still provides all of these secure, or not secure, but well-guarded metrics for parts per million, where that matters, and you'll actually see kind of parts per million in the photo because I was looking at one sensor that is based on parts per million, and eventually I switched over to using VOC because it's a slightly more stable sensor, and the VOC is actually in parts per billion, so I actually had to change that over. And so the basic idea is like you could end up running both, and you can measure one at parts per million and parts per billion, and the units of measure will not get mixed up in a way that will cause a problem. And there's, of course, lots of stories about that. We don't need to, but so, aside from the microprocessor story for .NET, there's also a way for .NET to be written into a CUDA core, for the warps for CUDA, and that is built with a library that before was called diff# that was specifically focused on the differentiation. Automatic differentiation. Sorry, it's too many terms. So this was brought forward as a hard fork that I'm currently the maintainer of, that was to get more literate compute and the ability to have a more natural notebook experience, and it's something we're still working on. But the really nice thing about this is that this goes significantly further than what PyTorch can do because of the levels of AD, automatic differentiation, that it can produce, and gives many more degrees of freedom and types of things that you can do within the ML world. But at the end of the day, you're still kind of limited to what CUDA can do, and a lot of what I'm looking forward to with the Fidelity Framework is for that targeting behind the scenes in LLVM that allows you to go to PTX and to those lower APIs below ROCm, that allows you to express custom kernels that are doing interesting things with math and with inference that you can't get out of the box with the APIs as they stand now. So here we are with our update to all of the name drops that have happened up to this point. Python's now been added because of the Python. There's two influences from Python on F#, and one was very early where F# departed from OCaml by getting rid of like line terminations and using indentation as scope as a way to manage the way that the semantics or syntax is managed within the app. And then the actual intentional mimicking of Python APIs within the diff# library, and now with Furnace, is another place where you could actually pull Python code out and make a few specific type changes, drop it into either diff# or Furnace, and it will just run. And that was an intentional design choice to make it as close to PyTorch as I could. So, time for another demo, and this is actually closer to what we're all here for, which is showing a little bit of a baseline for the, I want to make sure I'm bringing up the right thing. Yes, this is the, and I'm going to show one picture that hopefully is going to, let's see where the, this is already pre-compiled, so it'll run easily, but this is basically a .NET compiled version of Hello World. You'll notice it's 3.5 meg in size. The first version I did with .NET 9 was actually 6 meg in size because it was before they'd done optimizations. .NET 9 is still rolling out. So this is the AOT version of this that actually makes an executable, and the basic idea is it gets belts and suspenders, batteries included, everything from the system library gets put into this executable. So, and of course, if you run it, it does run, and so we'll do, there we go. So it's going to ask me what name is. So my name is Houston. It says, hello, Houston, yay, verily. So we're done with that portion of the demo. The second aspect of this is, and I want to make sure I'm doing the right thing. Yes. I was in the process of, let's do what? There we go. Yeah, okay. So you'll notice now this is the version of Hello World that I built with the direct line through MLIR and LLVM to whatever this platform is, you know, x86, Win64, whatever that triplet is for LLVM. And you'll notice that it's substantially similar where the .NET version AOT was 3.5 meg, this is 5.5K. It's a little bit smaller. So here we go with Hello World. Going to do the same thing. Here's to Houston. Yay, verily. So it actually does run. There's another example that I did, and the time library that's showing here, which is a common interface to talk to any of the platforms, Windows, Mac, or Linux, is here to basically to show that I'm also having to go and build all the libraries that instead of having the standard BCL library that's kind of that comfort food for everyone in the .NET ecosystem, I'm having to go back and rebuild that so that I can directly express it in source code and then be articulated within MLIR and then LLVM. So that's the good news, bad news. There's a trade-off with this where you're on your own, you get a lot more degrees of freedom, but the bad news is you're on your own, you have to build it. So there's a little bit of this, shown here, and then what happens now is there's a downstream effect of you can't rely on the assemblies of .NET to be this thing that you can go to NuGet and pull everything down. Of course, you can think about this, so there's a Java equivalent for this as well. So the basic idea is you're going to have to, and I, and the community people that are kind of coming in to save the day, are basically looking at Rust as a model for how to build an ecosystem for being able to manage packages, and it's source-based. This also comes from C and C++. So instead of cargo, I'm using Fargo because F# people love to put F in front of everything, as long as it's not vulgar. And so the basic idea is to build a series of components that can go and do all the things. Instead of NPM, we have FPM, et cetera, et cetera. But the basic idea is that there will be, in the same way that there are libraries that can either be compiled to Fable or into .NET, and they safely support either one, there will also eventually be a Fargo or a Fidelity version of those libraries that are just source-based that are sitting in its own repository. So they'll be accessible, and we'll be able to have shared interfaces with the other applications. So this is one of those little weird things of like, if you don't, if you haven't really pierced the veil in the compiler world, this will end up looking like spaghetti, and even if you have, it still looks like spaghetti. The basic idea is that there's still primitives within F# that are behind everything, even though I'm kind of hand-rolling some of those libraries. So F#.native interop has existed for a very, very long time, at least since F#2. And it gets used within diff sharp and the Furnace library and other places, and it really is a mainstay because that's the thing that eventually gets mapped to all the pointer usage that happens within the lowering through MLIR and LLVM. There are other things that kind of come into play, but that was one of the things that I wanted to show. Again, and you'll see that there's a lot of, over in the code sample over to the right, there's a lot of no warns. So this basically is saying, don't do the normal LSP thing of marking up my code as being wrong because I'm not doing normal .NET things. I'm not doing normal .NET things. Those warnings had been there for years, and I get to use all of them because in the development of a lot of the things for .NET that the F# folks have done, and Don Simon and many others, they actually had to go through the process of proving it to themselves before they could then go build it for the .NET framework. So a lot of these warnings, disabling and all the different switches and tags and toggles, those are extant. I get to lean right into it. So I don't feel like I'm really building a compiler. I feel like I'm taking F# compiler services and just running it edge to edge with MLIR and then continuing down from there. The first question that people often ask is why LLVM, and part of it is the fact that, while .NET is old enough to buy itself a drink at an American bar, LLVM has moved out of college and has gotten a respectable job and is overpaying for a condo somewhere in California. It's actually a little bit older than .NET and has a lot more industry backing behind it as well as community backing behind it now. And so the idea, I'm only interested really in the first few of each one of these lists, but inside of each one of these first two, like x86 and ARCH64, are triplets. There's all the different permutations and different things that it can actually target that are very specific to that environment. And again, those degrees of freedoms and that optionality means that you also have some burden within the framework itself to make sure that when you go in and access and target a particular platform, that you have the responsibility of honoring the way that platform manages memory and things like that. A good example is this is an ST Micro 32L5, which actually has a different memory structure than you would see in other ARM chips. And the basic idea is whenever you go and you build an alloy.memory implementation that's specifically for that target, there will be things that you'll do behind the scenes so that whenever you usher all of the memory mapping through MLIR and LLVM, that it will actually end up become bytecode and then instructions that can then be bootstrapped and run on the processor. So now we're going to talk a little bit about F#, F*. See, I just did it. And that is because we're getting close to being out of time. But to my point of what I was saying about types are better than tests and proofs are better than types. So many of you don't know what F* is, but everybody has used technology that F* has built. And that's because it's been used for TLS 1.3 and 1.2. A lot of the proofs for the QUIC protocol, for security around that, that was all DARPA, Microsoft, and F*. There's a ton of other stuff, and that's why this really super busy thing that looks like spaghetti is there. And down the little lower right-hand corner is what we care about, OCaml and F#. So that's the third demo, which is the one that really, I guess, people are going to care about seeing what the deal is between F* and F#. So here we have a, this is F*. I almost said F# and I caught myself because they do look so similar. But one of the interesting things about F* that it has both with dependent typing as well as the proof obligations that they take and they put in these functions is that's the significator of where to me it looks different. If you see what happens here, this has actually been validated and is currently being validated by the F* LSP. So it's just like any other live environment where if you make a change that causes something to be invalid, you end up getting an error. So essentially what happens here and where you're prima facie starting with F* code and then generating F# out of it is that you won't get F# code unless this is valid and the proofs pass. So it's it's a double-edged sword that cuts both ways. It's a freedom and a burden. I tend to think of it as a constructive constraint because now you get all of these nice things that then generate clean F# code that says, yay, verily this has been validated. And when you go and run I'll just do .NET run, good old-fashioned .NET run. What this does is it's just validating the fact that this validated code that's been generated is doing everything you're expecting it to do. So these little markup of different rules that fit different standards are kind of like the hello world version of verification. But they do substantiate that you can go from the process of having F* become your kind of benefactor and protector for the things that you actually build so that you are ensured that they are actually correct when they run on a chip. And this eventually gets into things around fintech and security and defense. And those are kind of peripheral to me at the moment. What I really wanted to do is to use these verifications to then inform the lowering process so that I knew that the construction that I was getting through MLIR was actually correct. And what's happening is we're actually running Z3 twice. The first time we're running Z3 is in F# before the code is actually generated, or while the code is generated in the LSP. Second time, it's actually being done here with these SMT asserts. That SMT is being called a second time inside of MLIR to call out, and then talking to SMTlib to then do that, like while we're going through the lowering process, assuring that, yay, verily this still fits within the constraints that we have for what we're planning to do with this code. Once that's done, at the MLIR level, you can then take, after that, the SMT asserts are fine, and you run opt_MLIR to verify that everything, yay, verily is still cool. You can now take and put these different constraints around those areas that you prove so that LLVM won't muck with it whenever it tries to go and do optimizations. So there can be areas of your code that are optimized at the MLIR level and end up in the abstract level within the what I call the program semantic graph that you no longer have to deal with, and LLVM is off the hook. This is two benefits. One is it makes the process faster because you're not forcing LLVM to optimize things that will end up causing you more cycles, more duty cycles and fixing. And the other side of course, is you're able to, at your option, export all those materials and certificates and actually bind them into the binary itself if you end up being in the industry that you need to produce a verified binary to then go to a certification lab that can then go through all the yay verily's and hallelujahs and everything for saying that it actually is a verified binary. So this is all opt-in, by the way. It's not something that's really required that you do, and in certain cases I want the compiler to do that for you behind the scenes so that those areas can already be validated and shown to be correct, and to provide options for optimization. This is actually, this kind of gets a little bit into my progress of getting garbage collection out of the runtime, or create a garbage collecting runtime adjacent to the binaries that I build. And I eventually backed out of it to just use Ray. And the basic idea is, from my experience with C and C++, to do as much manual memory management as possible, but put it within the framework in a way that makes it easier to deal with. The last bit was the connection to Haskell, which is using xparsec as the glue layer between F# and the semantic representation within the program semantic graph down into MLIR, that is actually using fparsec was actually a direct copy of parsec, which is a Haskell library, and this xparsec is like a more strongly typed version of that. So this is a super, super primitive thing that basically is saying that the transform that we're doing out of the semantic graph is safely becoming MLIR that you can then run and trust and do further lowerings on. So that actually covers everything. There is a story about the and beyond part of the title of this, where going to LLVM is really a control flow story, and going to GPUs, and the GPUs that are kind of adjacent to LLVM, even though LLVM can go to GPUs. But those direct to GPU out of MLIR, those are partial control flow and partial data flow stories. So you get into some of the, I think of TensorTorrent first because of their work with TT Forge and TT Metal, but there are others that have their own ways of using MLIR, either in-house for them to build solutions for their customers or building an API for developers to use. So these are all of these new hardware developers that are going beyond what I call the von Neumann or modified Harvard architecture, where the memory and the compute is very close to each other, and it's much more like a CGRA or FPGA architecture, where the data graph is being expressed in what in functional terms is referred to as pure functions. So that's the beyond part. Right now I want to stay very grounded with LLVM and this idea of this very small device being able to run code that can have a shared edge with .NET and with Fable, and for it to all run over a secure and low cost bandwidth connection. So that's my talk. Thank you for sitting through this and for listening and for letting me go over by a few minutes. There's a QR code there for the history of programming languages paper on F#, which talks about both the influences that came to it and the influences it exerts, and that process of the development of the language. So my name is Houston Haynes. I'm the founder of SpeakEZ Technologies, and you can find me online at speakeasy.tech. Thank you very much.